Hi guys, I'm going to be showing you today an example in chapter 5, number 5 actually, which is a probability chapter, pretty basic probability. So let me share my screen. And you are seeing, not me, but chapter 5, number 5, where's that go? Here it is. Okay, so we're given information in what's called a cross tabulation. We have 3 rows. Forget about the totals for a moment. This is the total, usually the totals on the right side. And we're asked to find various probabilities. So for example, how many 18 to 24-year-olds had said, I'm spending less time in the coffee house? The 3 categories are spending less time, the same time, that's the middle row, or more time. Well, 65 people are 18 and also spending less time. So 65 out of the grand total number of people who were questioned altogether, which was 1102. That's how you basically solve it. Let's go to the question. A person selected at random, what's the probability for between 18 and 24 who is also spending more time at the coffee house? Well, we just did that, more time. But it's 30 divided by 1102. Let me do that. 30 divided by 1102 is 0.027. And you round it to 3 places. This aside somewhere. 0.027. Check answer. And we got it right. Next question. This is just annoying. I'm not sure how to get rid of this. Maybe we'll make this bigger. That help? Maybe it helps. Among the 18 to 24-year-olds, what's the probability not spending more time? Well, if this is spending more time, not spending more time means either spending less time or spending the same time. So not spending more time. So it's 65 plus 77 divided by 1102. So 65 plus 77 equals, divided by 1102 equals 0.1288. So it's 0.129 when you round it off. 0.129. Uh-oh. What? Okay, let's see if I got what I got wrong here. Among, oh, okay, I'm sorry. See, I was tricked by what I was going to warn you with what comes later. When you say among means we're given for information about 2 variables simultaneously. So that's called conditional probability. And you can solve it by a formula, or you can sort of do it by common sense, which I'm going to recommend in this simple case, at least here. So among the 18 to 24-year-olds, so we're only talking about these 172 people. So it's 65 plus 77 divided by 172. So again, I think that was 65 plus 77 equals divided by 172. And that comes out to 0.8255 or 0.826. And this time my PhD came in handy. Okay, what's the probability that a person who spends the same amount of time at coffee houses, donut shops, is between 35 and 44? So we're talking about these 524 people who said they spend the same amount of time. How many are between 35 and 44? So it's 92 divided by 524. Which is 0.1755 or 0.176. Okay. Now, person responded they spend more time at a coffee house. What's the probability they're at least 65 years old? Okay. So we're talking about people who spend more time. So we're talking about these 110 people. 7 out of 110 are more than 65 years old. 7 divided by 110, that's 0.0636 or 0.064. Okay, they're not finished with us yet. What's the probability that a person who's at least 65 spends the same amount of time? Okay, so we're talking about people who are 65. How many spend the same amount of time? 71 out of 130. So this one will be 71 divided by 130, and that equals 0.546. Okay, so now comes the hardest part of the question, which is difficult to show you without a blackboard. We'll do our best. If not, we'll have to go to view an example. We'd like to know if the two variables are independent. Let's go back to the variables. Here's the data. So what that means is the following. If I would ask you how many people are 18 to 24, so you would say 172 divided by 1102. Right, that comes out to, let's say, I don't know, like 15%. And we even did that at the beginning. Okay, 15% for argument's sake. How many people just, but what if you know further information? What if, besides just asking that question in a vacuum, so to speak, just involving one variable, basically these totals over here, what if they said, I know for a fact the person's been spending more time at the coffee house. That means we're told further conditions, we're told further information about the other variable. If that changes things drastically, that would mean that they're related, because knowing one variable affects knowledge about the other variable. On the other hand, if it doesn't change, then they're independent. So let's see that. So how many people are between 18 to 24? It's 172 divided by 1102. That came out to 15.6%. Keep that in mind, 15.6. Well, let's round it to 16%. How many people are just generally spending, if you know for a fact the person was spending more time, how many are over 18? Well, 13 out of 172. 30 divided by 172 comes out to 17%. Well, 17% and, or they just say 16%, are pretty close. So knowing information about the other variable doesn't seem to drastically change it. So I'm going to say there, the answer is A. No. Let's see if I'm right. Oh. Okay, so they're being a little bit formal about it. They're saying if the numbers are not exactly the same, in other words, if the conditional probability is not exactly the same, and we said this was, I think we just said was 15.6%, and then the other one, what's that thing again? The conditional probability was 172 out of, I'm sorry, 172 out of 1102, which is 15.6%. And then I said, if you condition on this, you're going to get 30 divided by how many people? 30 out of 172, which was 17.4%. They're not exactly the same, and therefore the answer is yes, they're independent. The answer is they're not independent. This is it, because and this is the vertical line means conditional on, that if you calculated this probability, for example, given spend more time in the coffee house, it's not equal to the chance of being above 65 years old without being told that information. So the answer is B, and not equal. That's the trick here. So that's it. All right, guys, I'm sorry, I hope I didn't confuse you. Of course, you can always ask a follow-up question by emailing me or coming to class. Let's see what we're up to. Let's stop that. Let's close this down.